please subscribe to support the channel. You are not being pulled down right now. That feeling in your legs, that pressure in your feet, is not a force dragging you toward Earth. It is the ground pushing up on you, stopping you from doing what your body is trying to do by default. Move freely through space-time. Here's the straight version. In Einstein's picture, you live in a four-dimensional thing called space-time, three directions of space plus time. Massive objects like Earth don't send out a pulling force. They change the structure of space-time around them. In that structure, there are natural paths that free objects follow. These are called geodesics, but you can think of them simply as the straightest possible world lines through space-time. When you are in free fall, you are following one of those natural paths. No engine, no rocket, no muscle is pushing you along it. That is why an astronaut in orbit or someone falling in an elevator feels weightless. Their body is not fighting anything. When you stand on the ground, it is different. Your body wants to follow a free fall path, but the ground constantly pushes you away from it. Your muscles feel that as weight. The force on you is not gravity acting on your mass. The force on you is the support from the ground, stopping you from moving the way space-time is telling you to move. So then, what is that 9.8 meters per second squared number everybody memorizes in school? And where does this fit in this picture? Near Earth's surface, if you drop something and let it go, its speed relative to the ground increases by about 9.8 meters per second each second. In Newton's language, that's the acceleration caused by the gravitational force. In Einstein's language, that number describes how sharply the space-time around Earth is curved. It tells you how fast a freely falling path bends toward Earth in time. You can tie that to simple facts. Earth has a certain mass and a certain radius. For that mass and that radius, the curvature at the surface works out so that free fall looks like a change of speed of about 9.8 meters per second every second. Change the mass or the radius, and that number changes. Keep the same mass but squeeze it into a smaller radius. Now the space-time near the surface is more curved. If you stand on that surface, the free fall acceleration might be 20 meters per second or 100 depending how extreme you go. You feel heavier because the ground has to push harder to keep you from following the steeper natural path. Spread the same mass out into a larger, fluffier planet. The curvature at the surface becomes weaker. The free fall acceleration could drop to, say, 5 meters per second. On that world, you would feel lighter. Nothing mystical changed. The geometry changed, so the way free paths bend changed. That's all. Now, here comes the part that usually confuses people. If gravity near Earth is this strong geometric effect, and if that 9.8 number barely changes just above the surface, why do astronauts in the International Space Station float as if gravity does not exist? The station is only a few hundred kilometers up. Earth's radius is about 6,400 kilometers, so the station is not far away at all compared to Earth's size. If you work out the numbers, the free fall acceleration up there is still around 90% of what it is on the ground. If you could appear next to the station with zero sideways speed, you would fall down almost as hard as you do here. Astronauts are weightless for a different reason. The station is moving sideways at very high speed. As it falls toward Earth, its sideways motion carries it forward. Earth's surface curves away underneath at just the right rate, so instead of hitting the ground, it constantly falls around Earth. That is what an orbit is. You are always falling, but your path keeps missing the planet. Inside the station, everything shares that same free fall motion. The walls, the air, the astronaut's body, a loose screwdriver, a drop of water, all of them follow almost the same curved path through space-time. Since the astronaut is not pressed against a floor that pushes back, they feel no weight. Gravity up there is strong. The feeling of gravity is gone because the support force is gone. So now you might ask, is there any real way to tell the difference between standing in a gravitational field and just being pushed by a rocket? That was Einstein's big point. Put a closed box with no windows. Put it far away in deep space where external gravity is negligible. If rockets push the box with an upward acceleration equal to 9.8 meters per second, you will feel pressed to the floor with exactly the same weight as you feel on Earth. Light beams inside will bend in the same way. Objects you drop will fall to the floor. No local experiment inside that box can tell you whether you are in a rocket or parked on Earth. Turn off the rocket. Now you and the box drift freely. Inside, everything floats. That situation feels exactly like orbit or like free fall near Earth. Again, no local experiment can tell you whether you are coasting in empty space or falling toward a planet. This is called the equivalence principle. Locally, free fall is indistinguishable from being in a gravity-free region, and standing in a gravitational field is indistinguishable from being in an accelerating rocket. People turned this idea into real experiments. Drop towers lift a small lab and then let it fall. During the fall, the equipment inside is in free fall for a few seconds. Flames become spheres. Liquids form drifting blobs. Ultra-cold atoms form delicate patterns because any tiny push would show up clearly. Sounding rockets do the same thing above the atmosphere, giving minutes of freefall time. A lab that is falling behaves as if gravity has vanished, even though it is still close to Earth. That is the equivalence principle. But there's still a tougher question to poke at all this. How do we know gravity really treats all kinds of matter the same way? What if different materials had a slightly different gravitational response and we just never noticed? To test that, physicists use torsion balances. Picture a light horizontal bar suspended by a very thin wire, so it can twist easily. Put one material at one end, like aluminum, and a different material at the other end, like titanium. If Earth's gravity pulled a little harder on one material than the other, the bar would twist as one side was tugged slightly more. By measuring any twist, you would detect differences in how things fall. Modern versions of these experiments are incredibly sensitive. They can see differences in accelerations smaller than 1 part in 10 trillion. That means that if aluminum and titanium fell differently by even that tiny fraction, the device would notice. So far, every test shows the same result. Within that small error, different materials fall exactly the same way in a gravitational field. This is not an accident. It is deep evidence that gravity does not couple to some special charge the way electromagnetism does. It couples to mass and energy in a universal way. In the geometric picture, that means everything traces out free fall paths in the same curved spacetime as long as other forces, like electromagnetism, are not pushing on it. So by now, the basic picture is clear. What you call gravity is not really a pulling force. It is the effect of moving in a curved spacetime. You feel gravity only when something holds you off your natural freefall path. The familiar numbers like 9.8 meters per second squared are not magic. They're just describing how sharply that spacetime bends around the massive body. Astronauts float not because gravity turned off, but because they're finally allowed to move along those free paths. And careful lab experiments show that all kinds of matter obey the same rules to an absurd level of precision. That raises a new, sharper problem. If gravity is this weak geometric effect, how did we first measure its actual strength here on Earth and use that to weigh the entire planet using just 2 lead balls in a quiet room? How do you weigh an entire planet when you cannot leave the surface and you have no satellites, no electronics, nothing modern at all? At the end of the 18th century, Henry Cavendish did it in a quiet building that was basically a fancy shed. He set up a wooden rod about 2 meters long, hanging horizontally from a thin wire so it could twist. At each end of that rod, he attached a small lead sphere, only a few centimeters across. Then, on stands nearby, he placed 2 huge lead balls, each about 30 centimeters across and around 150 kilograms in mass. The only thing those big balls did was sit there and very slightly attract the small ones. No gears, no levers, no springs amplifying the motion, just raw gravity. The sideways pull between each big ball and each small ball was unbelievably tiny. We're talking about a force so small that everyday vibrations, wind, or footsteps would drown it out completely. That is why Cavendish worked in a sealed, quiet room and watched the apparatus with a telescope from the next room, so his own body would not disturb it. Over time, the gravitational attraction between the big and small balls caused the rod to twist a little against the wire. Now here's the crazy part. The ends of the rod only moved by a fraction of a centimeter. The deflection was on the order of a few tenths of an inch, less than a millimeter of sideways motion compared to the rod length. That's all. And from that tiny twist, Cavendish could work out the size of the torque on the wire, which told him the force between the balls. Why does that matter? Because Newton's law of gravity says the gravitational force between two masses depends on three things: how big the masses are, how far apart they are, and one universal constant that sets the overall strength of gravity. If you know the masses and the distance very accurately, and you can measure the tiny force between them, you can solve that relationship backward and figure out the constant. That constant is what we now call the gravitational constant, usually written as the letter g. In modern units, g is about 6.67 times 10 to the power negative 11. The units are cubic meter per kilogram per second squared. You do not need to memorize the units. The important point is how small that number is. Cavendish's result, using nothing but that rod, that wire, and those lead balls, was within about 1% of the best modern measurements. That is ridiculous precision for an experiment in a shed lit by candles. But Cavendish didn't care about the symbol G the way we do. His own description of the work was that he was weighing the world. Once you know the gravitational constant, you can combine it with measurements of Earth's surface gravity and radius to get Earth's mass. Here's the logic in plain language. At Earth's surface, the gravitational force on 1 kilogram is equal to that 1 kilogram multiplied by the familiar surface acceleration, the 9.8 number. Newton's law also tells you that same force must equal the gravitational constant multiplied by Earth's mass multiplied by that 1 kilogram divided by the square of Earth's radius. Put those two statements together and solve for Earth's mass. You end up with a value around 6 times 10 to the power 24 kilograms. That is the weight of the world, all from that tiny sideways tug between lead balls in a shed. This sounds like a historical curiosity, but it's not just a fun story. That constant G is still in every serious gravity calculation. When a spacecraft navigates to Mars, when your phone talks to GPS satellites, when we hang multi-kilogram mirrors inside the LIGO interferometers to detect gravitational waves, all of the orbital paths and forces are computed using that same gravitational constant that Cavendish effectively measured. Here's the uncomfortable part. We still argue about its exact value. Modern Cavendish-style experiments use better materials, vacuum chambers, laser readouts. They still get slightly different answers from each other. The differences are small, but not zero. For many constants in physics, like the speed of light or the electron's charge, we know their values so precisely that for daily work, they're basically exact. For G, the relative uncertainty is more like a few parts in 10,000 to 100,000. Among the fundamental constants, that's awful. So there's ongoing work where different teams keep reinventing Cavendish's basic idea with new tricks, trying to beat down the uncertainties. Tilted torsion balances, rotating attractor masses, atom interferometers that watch clouds of cold atoms respond to nearby masses. Every time someone publishes a new measurement of G, the community checks how it lines up with all the others and with Cavendish's old value, and the debate continues. All of this effort hammers home a deeper point that's easy to miss. Gravity is incredibly weak compared to the other forces of nature. Take two electrons. The electric force between them is repulsive and the gravitational force between them is attractive. If you compare their strengths, the electric force is about 10 to the power 36 times stronger than the gravitational attraction. That's a 1 with 36 zeros. Gravity is not just a bit weaker, it is crushed. This extreme weakness explains a lot about the universe you see. A small magnet on your fridge can easily overpower the entire Earth's gravity on a paperclip. To make gravity matter, you need huge amounts of mass, all with the same sign of gravitational charge, because there's no negative mass to cancel positive mass. Stars, planets, black holes, galaxies. You feel gravity strongly only when nature piles up absurd amounts of stuff. That weakness is also why some theorists suspect that gravity might not be confined the same way as the other forces. In some extra dimension ideas, the fields for electromagnetism and nuclear forces are locked to a three-dimensional slice of a higher dimensional space, while gravity can spread out into extra dimensions. If that were true, gravity would look diluted and weak in our slice. These models are highly speculative and have taken serious hits from experiments, but the basic puzzle remains. Why is gravity so much weaker than everything else? So, Cavendish's shed experiment did more than weigh the world. It exposed just how feeble gravity is between small objects, and how much mass you need before space-time curvature really shows its teeth. He nailed down the strength of the law that runs planetary orbits and satellite paths. But what happens when you push that law out to the orbit of a fast planet very close to the sun, and you ask for precise predictions over decades? Does Newton's gravity with Cavendish's constant really get every detail right, or is there a small crack waiting to show up? One planet in our own solar system quietly proved that Newton's law of gravity is wrong. Mercury orbits closest to the sun. Under pure Newtonian gravity, its orbit should be a stable ellipse that repeats forever. The line pointing from the sun to Mercury's closest approach point, the perihelion, should stay fixed in space except for small nudges from the other planets. When astronomers tracked Mercury over many decades and subtracted all those known nudges, they were left with a leftover twist. The perihelion slowly rotates by about 43 arcseconds per century. That's a tiny angle, but the data were solid. Newton's gravity could not account for it. People tried to save Newton. Some suggested there was an unseen inner planet, sometimes called Vulcan, tugging on Mercury. Others tweaked the inverse square law, adding small correction terms. None of it worked cleanly. Either you messed up the orbits of the other planets, or you could not quite hit that 43 arcseconds number without doing something ugly to the rest of the solar system. Mercury was a small, precise, this does not fit signal burning a hole in the model. This is where Einstein steps in with general relativity. Instead of gravity as a force, he gets a set of field equations that say mass and energy tells spacetime how to curve, and that curved spacetime tells planets and light how to move. When you solve those equations for the spacetime around the sun, you do not get a simple flat background with a force on top. You get a curved geometry, especially strong near the sun where Mercury lives. Now you take that curved geometry and you work out Mercury's orbit in it. You follow the path that a freely falling planet takes in that spacetime. When you do the full calculation, including the sun's mass and Mercury's orbital size and shape, you get an extra precession of the perihelion. The number that comes out is about 43 arcseconds per century. The anomaly that refused to go away in Newton's framework drops right out of Einstein's equations with no arbitrary patches. That match is not a vague, kinda close. It is a precise hit on a specific small effect that had been bugging astronomers for decades. At the time, that was a huge moment. It said, this is not just a prettier way to write the same thing. This is a deeper theory that makes different predictions and wins where Newton fails. But you could still say, fine, that is one weird planet. Maybe you can fudge Newtonian gravity with some complicated assumptions and get close to the same result. To really stress test Einstein's claim that gravity is geometry, you need something that is not about planets at all. You need to see what gravity does to light. In 1919, Arthur Eddington and his colleagues used a total solar eclipse to run that test. During an eclipse, the moon blocks the sun's glare, but the sun's gravity is still there. You can then take photographs of stars that appear close to the sun's edge in the sky and measure their apparent positions. If gravity bends light, those apparent positions should be shifted slightly outward compared to where the same stars appear when the sun is not in front of them. Einstein's general relativity predicted a specific angle for that deflection, about 1.75 arcseconds for starlight skimming the sun's limb. A simple Newton-style picture, treating light as little particles moving through a gravitational field, gives you only about half that value. This is a clean fork. Either nature chooses the general relativity number or it doesn't. The eclipse measurements were hard, the equipment was primitive by modern standards, and the atmosphere does not cooperate. But after careful analysis, the reported deflection was consistent with Einstein's prediction and not with the Newton half value. There were big error bars, but the central result pointed straight at curved spacetime. In the years that followed, better measurements with radio and then spacecraft tracking kept refining that deflection, and they all line up with general relativity. Now connect Mercury's orbit and those bent starlight rays. They are the same story told two ways. Near a massive, dense object like the sun, the geometry of spacetime is not flat. The paths that free objects follow in that geometry, called geodesics, are not straight lines in ordinary space. For a planet, that shows up as an orbit whose ellipse slowly rotates. For a beam of light, it shows up as a small bend near the limb of the sun. Nothing is reaching out and pulling in the old sense. There is no extra force of gravity acting on top of the geometry. The geometry itself is the law. Once you know the curvature, you know how things move, whether they have mass or not. That is why you can't fix Mercury by just adding a small force term to Newton's formula. Newton's picture assumes a flat background with forces acting in that background. Einstein is changing the background itself. It's like the difference between trying to fix a bad map by scribbling extra arrows on it versus realizing the surface you're mapping is not flat in the first place. So where does this leave Newton? Completely broken? Not quite. Newton's law still works absurdly well in a huge range of situations. For everyday engineering on Earth, for most satellite orbits, for the moon's path, the differences between Newton and Einstein are too small to worry about. As long as speeds are much lower than the speed of light and the gravitational field is not extremely strong, the curved spacetime of general relativity looks almost like flat space with a Newtonian force layered on top. In that regime, Newton is an excellent approximation. The key point is knowing where that approximation fails. Get close to a very dense mass or push speeds close to the speed of light, and Newton's picture quietly breaks. You start to see small anomalies like Mercury's precession, then bigger ones around neutron stars and black holes. Gravity is not just a bit more complicated. The entire answer to what is gravity has to flip from a pull between masses to the curvature of space-time itself. Once you accept that gravity is geometry, not a force, something even more unsettling comes up. If space-time is curved, it's not only space that's distorted. Time is baked into that structure as well. So if Mercury and starlight are already telling you space is not flat, what is gravity doing to the ticking of your own clock? And why does every GPS fix on your phone depend on Einstein being right about that? You carry a general relativity test in your pocket every day and probably never think about it. Every time you open maps and that blue dot snaps to your location, you're using a system that only works if Einstein is right about gravity changing the flow of time. GPS satellites orbit roughly 20,000 kilometers above Earth's surface. Each satellite carries multiple atomic clocks on board. Your phone listens to signals from several of those satellites at once. Each signal says, "This is who I am," and "This is the exact time when I sent this message." Your phone compares those timestamps, measures how long the signals took to reach you, converts that into distances, and then solves for your position. That only works if the clocks in space and the clocks on the ground stay in a very tight relationship. If we pretended that time ticks the same everywhere and ignored relativity, the GPS system would start to drift. At first, the errors would be small, but they would add up. After a day, your reported position would be off by kilometers. The fact that your location stays accurate to a few meters is direct evidence that we are not allowed to ignore relativity. So what exactly is gravity doing to those satellite clocks? Two effects fight each other. First effect, gravitational dilation. In general relativity, the closer you are to a massive object, the slower time passes relative to a faraway observer. A clock on the ground deep in Earth's gravitational potential ticks slightly slower than a clock high above Earth, where the gravitational pull is weaker. For GPS altitudes, the clock in orbit runs ahead of an identical clock on the surface by about 45 millionths of a second per day, purely because it's higher up in the gravitational field. Second effect, special relativity time dilation. Moving fast slows your clock compared to one at rest. GPS satellites are moving at several kilometers per second. That speed is much less than the speed of light, but it is enough to matter at the level of atomic clocks. This kinematic effect makes the satellite clocks tick slower than ground clocks by about 7 millionth of a second per day. Now, combine those two. Gravity speeds up the orbiting clock, motion slows it down. They do not cancel. Gravity wins. The net result is that each satellite's clock runs ahead of ground clocks by about 38 millionth of a second per day. That sounds tiny, so here's the important step: turning wrong time into wrong distance. Light travels about 300,000 kilometers in 1 second. If you convert that, it's about 300 meters in 1 millionth of a second. Multiply that by 38. In one day, if you did not correct for relativity, the satellite would think light had traveled about 11,400 meters more than it actually did. That's over 10 kilometers of position error building up every single day. Your phone uses signals from several satellites, so the geometry gets complicated. But the bottom line is simple. If the system did not include Einstein's corrections, the whole navigation network would fall apart. The engineers who designed GPS knew this from the start. The onboard clocks are pre-adjusted so that when they sit in orbit, with gravitational speed-up and motion slowdown both acting, they tick at the same rate as a reference clock on Earth. The software that computes your position also includes relativity in the equations it uses to combine the signals. So GPS is not compatible with general relativity as a nice bonus. GPS depends on general relativity. The system works because Einstein's description of gravity and time is stitched into its design. You could still say, fine, that's a complicated system. Maybe the engineers are just tuning numbers until it works. So here's the cleaner question. Does gravitational time dilation show up in direct, controlled experiments with clocks? The answer is yes, very clearly. Take two identical atomic clocks. Put one at sea level and put the other on a high mountain or in an airplane. Let them run for a while, then bring them back together and compare. The clock that spent time higher up in the weaker gravitational field will have gained a small amount of time compared to the one that stayed lower down. The difference matches the prediction from general relativity. Modern optical lattice clocks are so precise that you don't even need a mountain anymore. Raise one clock by a few tens of centimeters compared to another, and you can measure the change in ticking rate. The higher clock runs faster. Time really does pass at a different rate at your head compared to your feet, just by an extremely tiny amount. So, if clocks at different heights tick at different rates, what does that say about our idea of now? Relativity's punchline is that simultaneity is not absolute. There's no single global right now that all observers agree on. In special relativity, motion already messes with the ordering of events depending on who's moving. General relativity adds gravity to the mix. The presence of mass and energy curves space-time, and that curvature affects both distances and durations. Near Earth's surface, 1 second on your wristwatch is literally not the same physical interval as 1 second for a clock satellite high above, or for a clock near a neutron star, or for a clock floating far out in intergalactic space. You can relate them using the rules of relativity, but you cannot pretend they're all ticking in sync in some universal time. Every time your rideshare app shows your position correctly, it has silently solved this problem. It has taken signals from clocks that live in slightly different gravitational potentials and move at different speeds, applied relativity to translate between their time and your time, and then given you a coherent picture of where you are. The conspiracy here is that your daily tech quietly proves that gravity warps time and you barely notice. We started with the idea that gravity isn't really a pulling force, but a curvature of spacetime. GPS shows you that this curvature doesn't just bend paths in space, it also stretches and squeezes the flow of time itself. Once you accept that, another question opens up. If gravity can bend the path of time, what does it do to the paths of light across billions of light years? And can we use those distortions to see invisible matter and turn the entire universe into a gigantic lens? Here's the part nobody told you. The universe lies to you, your eyes. Mass doesn't just decide how things move, it decides where things look like they are. Take a massive galaxy cluster. Hundreds or thousands of galaxies, plus a huge cloud of hot gas, all packed into one region of space. According to general relativity, that whole mess curves spacetime. Light doesn't pass through that region in straight Euclidean lines. It follows the straightest paths in the curved spacetime, which, when you project them onto the sky, look bent. So when light from a faraway background galaxy passes near that cluster, its path gets deflected. By the time that light hits a telescope like Hubble or JWST, it's coming from a slightly wrong direction. On the image, the background galaxy shows up shifted, stretched, sometimes even split into multiple images. In deep images of clusters like Abell 2813 or SMAX 0723, you see long, thin blue or orange arcs. Those aren't weird spiral arms. Those are entire distant galaxies whose light has been dragged into arcs by the cluster's gravity on the way to us. This isn't a rare thing. The more massive and concentrated the cluster, the stronger the lensing. You can have weak lensing where background galaxies are just slightly stretched in a preferred direction. You can have strong lensing where they're turned into clear arcs and multiple images. In extreme cases, the distortion is so intense that the same galaxy appears several times in a ring around the cluster center. Now, take the special case where everything lines up almost perfectly. Background galaxy, lensing galaxy or cluster in front of it, and Earth all lie nearly on a straight line. In that configuration, light from the background galaxy reaches us along many symmetrical paths around the lens. On the sky, those paths form an almost complete ring around the foreground object. That's an Einstein ring. You have a bright central galaxy or cluster, and then around it, a thin circle of light. That circle is not a physical ring of matter. It's one galaxy seen in many directions at once because gravity bent its light all the way around the lens. Hubble images show beautiful, nearly perfect rings. Euclid and ground-based observatories have found many more. The key thing is this. The size of that ring is not random. The angular radius of the ring depends on how much mass is in the lens and on the distances between us, the lens, and the background source. If you know the distances, measuring the ring size tells you the total mass in the lensing object, with all the matter you can't see. No guesswork about how bright the stars are. Gravity is doing the accounting. Gravitational lensing isn't just an annoyance, it's a tool. It can actually boost our view of the distant universe. JWST's first deep field focused on the cluster SMAX 0723 for exactly this reason. The cluster's mass bends and magnifies the light from very distant background galaxies behind it. JWST's infrared vision is already sensitive to very faint and very old galaxies from when the universe was less than 1 billion years old. Add the cluster's lensing and it turns into a zoom upgrade. That's how JWST can pick out galaxies more than 13 billion years in the past. The cluster's gravity takes their light, which would otherwise be too faint to detect, and magnifies it. JWST can then record their spectra, measure their redshifts, and reconstruct their star formation histories. In plain terms, gravity is helping us spy on baby galaxies from the early universe. But those arcs and rings aren't just pretty lens tricks. They let you work backward and reconstruct how the mass is arranged in the foreground cluster. You start with a model of where the mass could be, then ray trace light paths through that curved spacetime and compare the predicted positions and shapes of background images to what you see in real data. You tune the model until the predicted arcs match the observed arcs. When you do that, seriously, the result is disturbing. The mass map you get from lensing does not match the light map. The visible galaxies and the hot gas seen in X-rays do not add up to the total lensing mass. There is extra mass spread in extended halos around the cluster that does not show up in visible light. It does not glow in X-rays. It is just there, affecting the geometry. This is one of the cleanest pieces of evidence for dark matter. Dark here does not just mean dim, it means not interacting with light at all, except through gravity. Lensing lets you see its gravitational footprint. Where the background arcs are strongest and most distorted, the underlying mass density is highest. Again and again, you find that the strongest lensing regions are not where most of the visible matter is, but where these invisible halos sit. Even in weak lensing, where each galaxy is only slightly distorted, you can measure the average alignment of those distortions across the sky. There is a preferred direction imposed by the foreground mass distribution. With enough galaxies, that tiny signal stands out from random orientations. You can turn that into a large-scale map of how mass, including dark matter, is spread through space. So, astronomy is no longer just about seeing light from stuff. Now gravity itself is part of the optics. Space-time has an effective refractive index. Regions with more mass bend light more strongly. When you look out at the universe, you're not looking through an empty transparent window. You're looking through a warped medium, and you have to undo that warping to find out what is really out there. Every arc in a cluster image is a direct demonstration that general relativity is not just a story for Mercury in GPS. It controls the way entire regions of the sky appear. It lets us weigh galaxies without touching them. It lets us detect invisible matter by the way it distorts distant background galaxies. And once you see that gravity bends light and draws mass maps that do not match the visible stuff, a bigger problem jumps out. If lensing says there's far more mass than you can see in clusters, what about individual galaxies? When you measure how fast their stars orbit around, does the visible matter explain those speeds, or is gravity again pointing to something hidden? Galaxies are spinning in a way that should tear them apart, and yet they stay intact. That is the first big red flag that the visible universe is not the full story. Take a spiral galaxy. You can measure how fast stars and gas clouds orbit at different distances from the center by looking at the Doppler shift of their light. Under normal Newton plus visible mass logic, the rotation speed should behave like this. Close to the center, speed rises as you include more enclosed mass. Once you move far out beyond most of the stars, the enclosed mass stops increasing much, so the speed should drop roughly like 1 over the square root of the distance from the center. In simple words, outer stars should move slower. But when astronomers actually plot these rotation curves, especially in spiral galaxies, that is not what they see. Far from the center, the speeds level off. The curve flattens. Stars way out in the faint outer disk orbit almost as fast as stars in the inner bright parts. With only the visible matter accounted for, those outer stars are moving too fast to be held in by gravity. Over cosmic time, the galaxy should fly apart. You can try to fix this by adding up every bit of visible mass: stars, gas, dust. The problem remains. The gravity from that visible matter is not enough. The simplest explanation is that there is more mass in and around the galaxy that does not show up in light. Not a little extra, a lot. Typically, you need about 5 times more invisible matter than visible to explain the flat rotation curves. That is one line of evidence. The next one is much harder to wave away because it comes from a giant, violent event, the bullet cluster. The bullet cluster is actually 2 galaxy clusters that have collided and passed through each other. When they hit, their hot gas components interact strongly, smashing together and slowing down. The galaxies themselves, which are mostly empty space, fly past each other with fewer collisions. X-ray telescopes show a bright blob of hot gas near the center of the system. That gas is most of the normal or baryonic matter by mass. So if normal matter is all there is, the main gravitational wells should sit where that gas is. Now, overlay that with a gravitational lensing map. Using the distortions of background galaxies, you can reconstruct where the total mass is, the same way we talked about before. In the bullet cluster, the strongest lensing peaks are not at the gas. They're offset, sitting near the galaxy concentrations on either side. In other words, most of the mass moved through the collision like the galaxies did, not like the gas did. So you have two pictures. One, normal matter, glowing gas, centered in one place. Two, total gravitational mass, revealed by lensing, centered somewhere else. If gravity came only from the bright gas and stars, those should line up. They don't. The mass inferred from gravity is separated from the visible mass. That is very hard to fake with just modified gravity laws. You would need gravity to behave in one way around gas and in another around collisionless matter, with just the right pattern to match the lensing map. Instead, the straightforward reading is this. There's a dominant component of matter that doesn't crash and heat up like gas does, and that doesn't emit light, but it still curves spacetime. When you study other mergers like MAX J0025 and similar systems, you see the same pattern. X-ray gas in one place, lensing mass peaks offset from it. Again and again, the data say the bulk of the gravitating mass is invisible in ordinary light. Combine this with galaxy rotation curves and with the way clusters hold on to fast-moving galaxies, and you get a consistent picture. To explain all of it, you need a form of matter that interacts very weakly with light, interacts with normal matter mostly through gravity, and adds up to about 5 or 6 times the total mass of normal matter. We call it dark matter, not because we know what it is, but because we know what it does. It curves space-time in the right way to explain the motions and the lensing. Now, scale this up. New missions like Euclid are scanning huge chunks of the sky, tracing tiny, weak lensing distortions in the shapes of millions of background galaxies. From that, they build three-dimensional maps of where the mass is at different distances, which also means different times in the past because of light travel time. Those maps include both normal matter and dark matter, but the dark part dominates the total. Over roughly 10 billion years of cosmic history, you can watch how structures grow. Small clumps of matter merging into bigger halos, filaments forming, voids emptying. Gravity is the main sculptor, and dark matter is most of the clay. Euclid's data, along with other surveys, turn gravity into a survey instrument for the dark sector. You don't have to see dark matter directly, you just follow how it bends light and how it drags normal matter around. So here's the reversal. For a long time, we thought stars and gas were the real content of galaxies and clusters, and gravity was just the consequence of their presence. The new view is almost the opposite. The main gravitational architecture is made by invisible dark halos. The bright stars and gas just collect in the deepest parts of those invisible halos, like lights installed along the tops of an already existing structure. When you look at a spiral galaxy, you're not seeing the bulk of its mass. You're seeing a thin, glowing disk sitting inside a much larger dark halo that sets the gravitational potential. When you look at a cluster, you're not seeing most of the stuff holding it together. You're seeing tracer material floating in an invisible well. Dark matter changes the question from why isn't gravity strong enough to something sharper. Where did all that structure come from in the first place, and how did gravity and dark matter take a nearly smooth early universe and build this giant web of clusters, filaments, and voids we see today? To answer that, you have to roll the clock almost all the way back to the beginning, stare at the universe when it was less than 500,000 years old, and read tiny temperature ripples as the blueprint for everything gravity later built. How do you get from a young universe that is almost perfectly smooth to the insane structure you see now? Galaxies, clusters, and a giant cosmic web stretching for billions of light years. That sounds impossible at first glance because the starting point was shockingly uniform. The evidence is in the cosmic microwave background, the CMB. This is the leftover light from when the universe was only about 380,000 years old. Back then, the universe was a hot plasma of electrons, protons, and photons all tightly coupled together. When it cooled enough for electrons and protons to form neutral atoms, photons could finally travel freely. That flash is still around today, stretched by expansion into microwave wavelengths with a temperature of about 2.7 Kelvin. Early on, people thought the CMB was basically perfectly smooth, same temperature in every direction. Then satellites like COBE, then WMAP, then Planck mapped it much more precisely. They found that the temperature is not exactly the same everywhere. It has tiny fluctuations, hotter and colder patches at a level of about 1 part in 100,000. If the average is 2.7 Kelvin, the variations are only tens of microkelvin above or below that. That sounds like noise, like nothing, but those tiny temperature bumps are not random junk. They correspond to small differences in density in the early plasma. Slightly hotter spots are slightly lower density. Slightly colder spots are slightly higher density. So the early universe was not perfectly smooth. It had very small overdense regions and underdense regions. Now, here's the key chain. A region that is a little denser has a little more gravity. That extra gravity pulls in more matter from its surroundings. As more matter falls in, the overdensity grows. It becomes even denser, and its gravitational pull becomes even stronger. Over time, this positive feedback turns a tiny bump into a large structure. Run that forward for billions of years, those tiny 1 in 100,000 density bumps grow into the large-scale structure, galaxies, clusters, and the filaments between them. Underdense regions go the other way. They lose matter to their neighbors and become voids. So the CMB is not just a baby picture of the universe. It is a blueprint. It tells you where future structure will form more easily. But the early universe was not a simple playground for gravity. There were 3 major effects fighting at the same time. Gravity tried to make matter clump. Radiation pressure, the push from photons on the plasma, tried to smooth things out. Cosmic expansion tried to stretch everything and dilute it. In that hot plasma, gravity pulled matter inward, compression raised to pressure, and that pressure pushed matter back out. This back and forth created acoustic waves, real sound waves in the early universe fluid. Those waves leave a specific pattern in the CMB temperature map, a series of peaks and troughs in the power spectrum when you plot fluctuation strength versus angular scale on the sky. You can calculate what those acoustic peaks should look like for different mixtures of normal matter, and dark energy. If you increase normal matter, you change the relative heights of certain peaks. If you change dark matter, you shift others. If you change the geometry of the universe, you alter the overall pattern. The observed CMB power spectrum is like a fingerprint of all these ingredients and the rules gravity followed. Planck and its predecessors measured that fingerprint with ridiculous precision. The temperature anisotropies are mapped down to a few arc minutes with accuracy of a few parts per million. When you fit general relativity plus a universe made of normal matter, and dark energy to that data, several things fall out. First, the spatial geometry of the universe is extremely close to flat. That means if you draw a giant triangle with sides made of light rays, the angles add up to 180 degrees, to within about 1%. That is a statement about how gravity has curved space on the largest scales. Second, the best fit composition looks like this: about 5% normal matter, about 27% dark matter, and about 68% dark energy. That's the now standard 5-27-68 split. This is gravity, in the language of general relativity, writing its own autobiography in the CMB. It tells you, here's how much stuff there was, here's how curved spacetime was, here's how structure started to grow. The shocking part is how little it needed at the start. Those tiny fluctuations in density were only 1 part in 100,000. If you had just looked at that number without understanding gravity's long-term effect, you might have said that's too small to matter, but it was enough. Given billions of years, the slight advantage of slightly denser regions compounds. Gravity keeps pulling. Dark matter, which doesn't feel radiation pressure the way normal matter does, starts clumping earlier and deeper. Normal gas falls into those dark wells later and cools and forms stars. Over time, those tiny ripples turn into galaxy halos, clusters, and the entire cosmic web network of filaments and voids mapped by surveys. No conscious design, no special pattern maker, just small statistical fluctuations plus a law of gravity that says mass attracts mass in an expanding spacetime. The weird thing is not that the universe ended up with structure. The weird thing is that you can trace that structure back to temperature blips of a few tens of microkelvin on the sky. So now you have this picture. Dark matter and gravity team up to grow structure from tiny seeds. Normal matter rides along, lights up the densest regions, and you get the web. The CMB acoustic peaks and the large-scale structure maps both match one and the same model. But there's one more twist hidden in that same data. When you follow the growth of structure forward and compare it with how fast the universe is expanding at different times, you find something unsettling. Gravity is not winning forever. On the largest scales and at late times, some other component starts to dominate and push everything apart faster and faster. If gravity is the architect that builds the cosmic web, what's the thing that billions of years later starts to pull the scaffolding apart and make the expansion speed up instead of slow down? For most of the 20th century, the big argument was pretty simple. Is gravity strong enough to eventually stop the expansion of the universe, or will the universe expand forever but slow down as gravity fights it? Both sides agreed on one thing. Over time, expansion should decelerate. Gravity always pulls things together. That was the basic assumption. Then in the late 1990s, two teams went and checked. They used Type 1a supernovae, special exploding stars that have nearly the same intrinsic brightness as distance markers. If you know how bright something really is, and you measure how bright it looks, you can work out how far away it is. They measured supernovae in galaxies billions of light years away and compared distance with redshift, which tells you how much the universe has expanded since the light was emitted. Here's the punchline. The supernovae were too dim, dimmer than they should have been if the expansion had just been slowing down under gravity. Dimmer means farther. The distant galaxies were farther than a decelerating universe could explain. The only consistent way to read that data was brutal. The expansion is not slowing down, it's accelerating. The universe is not just coasting, it's accelerating. That result smashes the idea that gravity always wins on the largest scales. If gravity were the only big effect, expansion would slow as matter pulls on matter. Instead, something with the opposite effect is dominating at long distances. In the equations of general relativity, this shows up as a kind of negative pressure, or a term that acts like a repulsive contribution to the dynamics of the universe. We call the phenomenon dark energy. The simplest version is a cosmological constant. In words, there's a constant energy density built into empty space itself. Even when you remove all matter and radiation from a region, the vacuum still has a non-zero energy. In Einstein's equations, that acts like a term that pushes spacetime to expand faster. Now combine those supernova results with everything else we talked about: the cosmic microwave background, large-scale structure, baryon oscillations, lensing surveys. When you fit one model to all of it, you end up with a specific mix that people call the lambda cold dark matter model, usually shortened to lambda CDM. Lambda stands for the cosmological constant piece, the dark energy. Cold dark matter is the slow-moving dark matter that clumps and seeds structure. In that model, today's universe breaks down roughly like this: about 5% normal matter, about 27% dark matter, and about 68% dark energy. So the stuff you actually see, stars and gas and dust, is just a small slice. Dark matter is the main gravitating material building halos and webs. Dark energy is the dominant ingredient in the energy budget and controls the long-term fate of expansion. On the scales of galaxies and clusters, normal gravity still runs the show. Dark energy is very smooth and only really matters when you average over huge distances. On those huge distances, though, dark energy takes over the Friedmann equations, the ones that describe how the scale factor of the universe evolves with time. Instead of the scale factor's growth slowing down, the dark energy term makes its second derivative positive. In plain language, the expansion rate speeds up. This leads to a weird but important point. In general relativity, you don't bolt on a new anti-gravity force. You don't invent a new particle that pushes things apart. A positive cosmological constant is just another way spacetime can be curved. Matter and radiation curve spacetime one way, vacuum energy curves it another. The math is the same framework, you just admit that the vacuum can have its own energy density and pressure, and that changes how the whole universe evolves. So gravity, as a theory of space-time geometry, is still the language you use. Dark energy is not outside gravity. It is one of the allowed types of source terms in gravity's equations. The part we misunderstood was assuming that gravity's only role was to attract and slow things down. The full theory allows a component that causes accelerated expansion when it dominates. The disturbing part is what this means for the future. If dark energy is really a constant property of space, and if its value stays the same over time, there is no big crunch. The universe will not turn around and collapse. Instead, the expansion keeps accelerating. Distant galaxies cross a kind of horizon where their light can never reach us. Over very long times, more and more of the universe slips out of causal contact. Locally, inside galaxies and clusters that are already bound by their own gravity, not much changes. Stars age and die. Black holes slowly merge. Gravity still holds those systems together, but on the largest scales, everything else races away. The sky gets emptier. Future observers, living trillions of years from now in some galaxy remnant, might not even be able to tell there was once a hot Big Bang, because all the external evidence will have redshifted beyond detection. So, gravity is not the final where everywhere. It shapes matter into galaxies and webs, but then, on the biggest scales, it gets overwhelmed by this smooth, dark energy component. You end up with a universe where gravity is strong inside isolated islands of matter floating in an ever faster expanding sea. Here is the next uncomfortable question. If spacetime is flexible enough to curve, to expand, and even to accelerate its expansion, what happens when massive objects slam together? Does the geometry just quietly adjust? Or does spacetime itself ring, sending out waves we can actually detect? If you shake an electric charge, you get light. That's basic electromagnetism. General relativity says something similar but more extreme. If you move mass around in the right way, you don't just bend space-time statically, you send ripples through it. Not waves in some medium sitting inside space, but waves of space-time itself stretching and squeezing as they pass. There's a catch. If you just move something in a perfectly symmetric way, the effects cancel out. You need an accelerating, lopsided mass configuration. Two stars orbiting, a collapsing asymmetric core, two black holes spiraling in. The equations say these systems radiate energy as gravitational waves. Those waves travel at the speed of light, crossing the universe, carrying information about the motion that created them. For decades, this was a nice-in-theory prediction. Einstein himself wasn't sure gravitational waves would ever be detectable. The effect is insanely tiny by the time it reaches us. You're trying to measure a fractional change in distance so small that it makes atomic scales look huge. People wrote down designs and did back-of-the-envelope calculations, and many of them thought, this is hopeless. Then, LIGO switched on. On September 14, 2015, the two LIGO detectors, one in Washington State and one in Louisiana, both saw the same very specific signal. It lasted about 0.2 of a second. In that short time, the frequency rose from around 35 cycles per second to around 250, and the amplitude grew and then cut off sharply. If you convert that into sound, it's a little chirp that slides upward and then stops. When you fit that chirp with general relativity's predictions, you get a clean story. Two black holes, one about 36 times the mass of the Sun, the other about 29 solar masses, were orbiting each other, losing energy to gravitational radiation, spiraling together, and finally merging into a single black hole of about 62 solar masses. The missing 3 solar masses worth of energy went into the waves themselves as pure gravitational radiation. That energy was released in a fraction of a second. For that instant, the power output in gravitational waves was greater than all the stars in the observable universe radiating light combined. And we picked up the leftovers on Earth more than 1 billion years later as a tiny tweak in the lengths of metal tubes. LIGO is basically a giant ruler. Each detector has 2 tunnels, 4 kilometers long, arranged at right angles. A laser beam is split and sent down both arms, bounces back and forth many times between mirrors, and then recombines. If the arms are exactly the same length, the interference pattern cancels out at the detector. If one arm becomes even slightly longer or shorter relative to the other, the interference pattern shifts and the detector output shifts. A passing gravitational wave stretches space along one arm while squeezing it along the other and then alternates. The strain that LIGO is sensitive to is around 10 to the negative 21. That is a fractional change in length of 1 part in 1 billion trillion. Over 4 kilometers, that means a change in arm length of less than 1,000th the diameter of a proton. Another way to say it, it's like changing the distance to the nearest star outside our solar system by about the width of a human hair and trying to measure that. And yet, with enough laser power, enough isolation from noise, and enough clever data analysis, we can see that change. Once the first detection was confirmed, more started coming. Black hole mergers of different masses, some heavier, some lighter. Events where one black hole might be spinning rapidly and tilting the orbital plane. Then a neutron star merger that not only rang LIGO and Virgo, but also lit up telescopes across the electromagnetic spectrum. The gravitational wave catalogs now contain hundreds of events. From some of these signals, physicists have tested general relativity's predictions in extreme regimes. The late-time ring-down of the merged black hole, where it settles into its final shape, can be compared to the allowed vibration modes of a Kerr black hole, the rotating solution in GR. By checking how the horizon area changes, they have tested Stephen Hawking's area theorem. The total event horizon area of black holes should never decrease in any classical process. The data so far are consistent. The final horizon area is always at least as large as the sum of the original areas. So gravitational waves are not just a proof that ripples exist. They're a new way to look at gravity itself in situations where space-time is being violently rearranged. There's another piece you should notice. We used to talk about space as if it were a static stage. Matter moves, fields change, but the background just sits there. General relativity already broke that idea by saying space-time can curve. Gravitational waves go further. They say space-time is a dynamic field that can carry energy, momentum, and information as waves. Space is not passive. It can vibrate. And space is not quiet. We just didn't have the ears to hear it. Black holes are colliding. Neutron stars are smashing together. Probably entire populations of binary systems all across the universe are constantly sending out overlapping waves, forming a gravitational wave background. Our current detectors are just sensitive enough to catch the closest and loudest events. Future detectors will hear the rest of the orchestra. Lower frequency roars from supermassive black holes, faint murmurs from white dwarf binaries, maybe even hints of processes from the early universe itself. So gravity has upgraded from thing that keeps your feet on the ground to thing that carries its own form of radiation across the cosmos. It bends light, shapes time, and now we've confirmed that also rings when massive objects move in just the wrong way. But all of this still leaves one uncomfortable question open. We are detecting the depths of black holes by listening to space-time vibrate. Can we directly see the regions where gravity is so strong that not even light escapes? Are event horizons real visible features of the universe or just a mathematical trick in the equations? Black holes used to be the monsters that lived only in equations. You could write them down on paper, you could talk about event horizons and singularities, but they felt like theoretical ghosts, not actual things you could point a camera at. That changed when we finally built a telescope the size of Earth. The Event Horizon Telescope is not one single dish. It's a network of radio telescopes spread across the planet, all pointing at the same target and recording signals with atomic clock precision. Later, those recordings are combined using a method called very long baseline interferometry. In plain language, you use Earth's diameter as your effective telescope size. That gives you angular resolution sharp enough to pick out details the size of a few tens of micro arcseconds, which is like being able to read a newspaper in New York from Europe. In 2017, that global array stared at the center of the galaxy M87, a giant elliptical galaxy about 55 million light-years away. At its core lives a supermassive black hole we call M87 star. When the EHT team processed the data, after brutal amounts of calibration and imaging work, a consistent picture emerged. A bright, slightly lopsided ring of emission, and inside that ring, a dark central region, a shadow. The ring is roughly 40 microarcseconds across on the sky. That's tiny, but for a black hole at that distance, it matches what general relativity predicts. Plasma around the black hole heats up and emits radio waves as it spirals in. Light that skims close to the black hole can orbit a few times in a region called the photon sphere before it escapes. Those complicated paths pile up into a bright ring. Rays that cross too close to the event horizon never come out. That missing light shows up as a darker inner patch, the shadow. You can take the equations for a rotating black hole, called a Kerr black hole, plug in a mass of about 6.5 billion suns, place it 55 million light-years away, simulate how light bends around it, and see what image you'd get. The result lines up with the EHT observation. Ring size, overall shape, and the fact that it's brighter on one side because material is moving toward us there and gets Doppler boosted. That's not a cartoon version of general relativity. That's the theory surviving a direct, brutal test at the edge of what's possible. The mass you infer from the ring size, about 6.5 billion times the mass of the Sun, also matches measurements from completely different methods, like tracking stars and gas orbiting in the central region of M87. So you have dynamic evidence and imaging evidence, both pointing at the same monster. You might say, okay, maybe we got lucky with one supermassive black hole that happens to cooperate. So the EHT team went after a harder target, the black hole at the center of our own galaxy, Sagittarius A star. Sagittarius A star is much closer, only about 27,000 light-years away, but also much smaller, about 4 million solar masses. That combination makes it imaging harder, not easier, because the material around it can change on timescales of minutes. During a single observing run, the source is already varying, which smears the image if you treat it as static. The EHT team had to develop new imaging strategies to handle that variability. In 2022, they released the image. It's fuzzier than M87, but the basic structure is the same. A ring of emission with a darker central region. The ring size matches what you expect for a 4 million solar mass Kerr black hole at that distance. The fact that both a 4 million solar mass black hole and a 6.5 billion solar mass black hole produce the same ring plus shadow pattern, scaled properly, is a huge confirmation that general relativity's description works across an enormous range of masses and environments. M87 gives you another bonus. It powers an enormous relativistic jet, a narrow beam of plasma shooting out from the galaxy's core for thousands of light-years. That jet has been seen at many wavelengths for decades. What EHT added were polarized images, maps of how the radio waves are oriented. Polarization carries information about magnetic fields. Those images show ordered magnetic field structures very close to the event horizon. That tells you that magnetic fields are threading the accretion flow and are likely involved in extracting rotational energy from the black hole and launching the jet. So near the event horizon, you have an extreme partnership, gravity curving space-time and setting the overall geometry, and magnetic fields plus plasma physics taking that setup and turning it into a jet that shakes entire galaxies. So we're not just seeing a blob, we are resolving the region where light orbits, falls in, or escapes, and seeing structures that match detailed simulations based on general relativity plus magnetohydrodynamics. That's as direct as it gets for an object that, by definition, does not let light out from inside its own horizon. For a long time, skeptics could say event horizons are just features of the math. Maybe real objects never reach that extreme. Now we have timing data from stars orbiting Sagittarius A that require a very compact, massive object. We have gravitational wave signals from mergers that match black hole waveforms. And we have actual images showing a shadow whose size and shape match the predictions for a horizon-sized region. Put all of that together and it's hard to avoid the conclusion. Event horizons are not just lines in a textbook diagram. They are real boundaries in space-time that we can probe observationally from multiple angles. Gravity's wildest prediction, a region from which not even light can escape, has turned into something you can put on a slide in a talk or in a thumbnail on a video. That creates a sharper tension. On the one hand, general relativity keeps passing these extreme tests: Mercury, GPS, lensing, black hole shadows, gravitational waves. On the other hand, the entire framework rests on a simple principle, that gravity is not really a force. It's the result of all forms of mass and energy responding the same way to space-time curvature. If that equivalence ever fails, the whole structure cracks. So the next logical move is obvious and risky. Push as hard as possible on that principle. Drop different materials, twist delicate torsion balances, fly exquisitely calibrated masses in space. If anything, anywhere falls differently, then black hole images, GPS, everything we've built on top of general relativity has to be rethought. If a hammer and a feather hit the ground together in a vacuum, what is that actually telling you about gravity? It's not, wow, that's neat. It's a direct punchline. Gravity treats all bodies the same way, no matter what they're made of. In everyday life, air ruins the effect. A feather falls slower because air pushes up on it more than on a hammer. Take the air away and let both objects fall only under gravity. On the moon, in that famous Apollo 15 demo, they landed at the same time. That is not a coincidence. It means two things are equal for both objects: their resistance to acceleration when you push them, inertial mass, and the charge they have for gravity, gravitational mass. In Newton's formula, those two masses could in principle be different. In reality, all the experiments say they're the same to incredible precision. The hammer-feather drop is a dramatic version. The really hard tests use torsion balances based on Etwutz's design. You hang a horizontal bar on a thin wire. Put one material on one end, a different material on the other. Earth's gravity pulls on both. If they feel slightly different gravitational acceleration, the bar twists as Earth pulls one side a bit more. By watching that twist as you rotate the device relative to Earth, you can tease out tiny differences. Modern versions of this setup show that different materials fall the same way to within a few parts in 10 to the power 13 or even 10 to the power 14. That means if two test masses had even the tiniest difference in how gravity acted on them at that level, we would have seen it. So if every material you try accelerates identically in a gravitational field, what does that say about what gravity actually is? It says gravity is not a usual force, at least not in the way electromagnetism is. With electromagnetism, different charges feel different pulls. Positive charges go one way, negative charges go the other way. Neutral particles are mostly unaffected. You can't transform that away. Gravity is different. If all test bodies accelerate in exactly the same way, you can always find a reference frame where that acceleration disappears locally. That's the logic behind the elevator idea. If you're in a closed box in freefall, everything around you floats. Inside that box, there's no experiment you can do that'll tell you there's a big gravitating mass outside pulling on you. The equations simplify. Motion in that frame looks like motion in special relativity with no gravity term. General relativity takes that seriously and promotes it to a principle. In GR, an object in free fall is not under a force of gravity. It is following a natural force-free path in spacetime, called a geodesic. Gravity shows up when you insist on using a frame that is held up, like standing on the ground, where you constantly feel the support force, not the pull. So if that equivalence between free fall and no gravity is the core pillar, what happens if it ever fails for even one type of matter? That would be huge. If you could show that beryllium falls differently from titanium in the same gravitational field, or that normal matter and antimatter respond differently to Earth's gravity, you would have found a direct crack in general relativity. People are hunting exactly that. On Earth, torsion balances compare all sorts of material pairs, aluminum against platinum, beryllium against titanium, and so on. The differential acceleration is consistent with zero down to insanely small levels. In space, the microscope mission took this further. It flew 2 test masses of different composition inside a satellite and let them free fall around Earth together, shielded from most disturbances. The instrument measured whether one mass needed a slightly different electrostatic force to keep it centered than the other. If so, that would mean gravity was pushing on them differently. The result? No detectable violation. The difference in acceleration is constrained again at the parts in 10 to the power 15 level. As for antimatter, early measurements with antihydrogen are far less precise, but so far do not scream falls upward or anything exotic. Inside the error bars, it behaves like normal matter. If gravity couples universally like that, then maybe the equivalence holds, but the detailed distance law breaks instead. So people hammer on that too. Newton's law says the strength of gravity between 2 point masses goes like 1 over the distance squared. Double the distance, the force drops by a factor of 4. Some theories with extra dimensions or new short-range forces predict that at very small separations, this rule would change. The effective force might fall off faster or slower. You can model that as extra terms that only matter below, say, 1/10 of a millimeter. To test that, experimenters again used torsion balances, but now with carefully shaped attractor masses brought extremely close to the test masses at separations of a few tens of micrometers. They look for any deviation from the expected torque if the force law were pure inverse square. These experiments are painful to do. You have to control electrostatic forces, magnetic contamination, thermal drifts, seismic noise. But after all that, the result is boring in the best way possible. Newton's 1 over distance squared behavior still holds down to around 50 or 60 micrometers. A whole chunk of proposed easy extra dimension models is ruled out by those null results. Given how weak gravity is, you'd think it would be the easiest place for new physics to show up. A tiny extra interaction should be enough to compete with gravity at short distances. A small difference in how 2 materials fall should be enough to tip the balance. Instead, gravity is stubborn. The equivalence principle keeps surviving tests across many compositions and environments. The 1 over distance squared law keeps working down to 1,000 times smaller than the thickness of a human hair. That stubbornness has teeth. Any new theory of gravity, whether it adds extra fields, extra dimensions, or tries to merge gravity with quantum mechanics, has to reproduce this precision. It can't just casually say, oh, and at short distances, things change a lot. The changes have to be subtle enough to hide under all these constraints, or else they're simply wrong. So gravity looks fake in the sense that in the right frame, you can transform it away and think just in terms of geometry. But it's a fake force that refuses to break under direct attack. We've dropped every kind of matter we can, twisted delicate balances in labs and in orbit, and the result so far is the same. Everything falls the same, and the field obeys the same simple distance law down to incredibly small scales. But there's still one more obvious place to push: shrink the experiment itself. Instead of big lead balls and kilometer-scale setups, can you probe gravity in the lab with tiny test masses, millimeter and micrometer separations, and look for deviations or new effects that all the previous tests somehow missed? You'd think that if gravity was going to break, it would break in a small, controlled lab before it breaks in a black hole. So people have been attacking it on the workbench, with setups way more delicate than Cavendish's lead balls. Modern small-scale gravity experiments don't use giant spheres in a shed. They use tiny test masses, carefully machined metal disks, thin membranes, even clouds of ultra-cold atoms. The goal is simple and brutal. Bring masses very close together, at separations from millimeters down to tens of micrometers, and see if the attraction between them follows Newton's 1 divided by distance squared rule perfectly, or if there's even a tiny deviation. Why care about that range? A lot of speculative ideas live there. Extra spatial dimensions that only show up at short distances. New short-range forces that act like gravity but die off very fast with distance. Ultra-light dark matter that can make the gravitational potential wiggle over time or space. On paper, these things can tweak the gravitational pull at small separations without wrecking everything we know about planets and galaxies. So tabletop experiments are the obvious way to hunt them. One of the most famous groups doing this is the UTWASH team at the University of Washington. They've built a series of torsion balances that look simple but are insanely engineered. A typical setup uses a thin, horizontal disc with holes or cutouts in a specific pattern, hanging from a fine fiber. Below it sits another disc with a matching pattern of dense metal sectors. When you rotate the lower disc, the gravitational attraction between the patterns creates a tiny twisting torque on the upper disc. If gravity followed exactly the 1 over distance squared law, that torque as a function of angle is predictable. By bringing those disks within fractions of a millimeter of each other, they can test the law at very short distances. They've pushed this down to separations of around 50 micrometers. That's about 1/20th of a millimeter, thinner than a human hair. At that scale, any extra force that falls off faster than gravity or adds a small bump in the potential could show up as a mismatch between the measured torque and the Newtonian prediction. The result so far, a pure 1 over distance squared potential, still fits the data extremely well even at those tiny gaps. The team parameterizes possible deviations as an extra term that adds a short-range correction with an exponential falloff. For a whole range of strengths and length scales around tens of micrometers, those corrections are just ruled out. They would have changed the torque in ways that are not seen. That wipes out a big chunk of easy extra dimension models, where gravity briefly gets stronger or weaker at short distances because some of its field lines leak into hidden directions. If those effects were large enough to explain, say, the weakness of gravity compared to other forces, they should have shown up in these tests. They didn't. There's another reason people obsess over this tens of micrometers window, the so-called dark energy length scale. You can construct the length scale from the observed dark energy density, and you get a number of order tens of micrometers, often quoted around 85 micrometers. Some theorists took that seriously and said, maybe the same physics that gives you dark energy also modifies gravity around that length. If that were true, you might see tiny deviations from Newton's law right around that scale. So far, nothing. Experiments probing down to 50 or 60 micrometers have not seen any clear bend in the force law. Gravity just keeps behaving as if it's a simple inverse square attraction at those distances. No obvious resonance, no fall-off change, no extra push. Whatever dark energy is, it is not announcing itself as a simple, sharp modification of gravity at tens of micrometers. And it's not for lack of trying. People are not just using torsion balances. There are experiments with micro-cantilevers, where a tiny beam bends under the pull of a nearby mass. There are setups with atom interferometers, where you split a cloud of cold atoms into two paths, let one path pass closer to a test mass, and then recombine them and look for a phase shift from the different gravitational potential. There are optomechanical systems, where a small mirror or membrane feels the attraction of a neighboring mass, while lasers read out its motion at absurd precision. Across all of these, the pattern is the same. Within current sensitivity, gravity behaves itself. No clear evidence for new short-range forces, no wobble that screams ultra-light dark matter is shaking the potential here, no smoking gun for gravity leaking into extra dimensions at a tenth of a millimeter. This is the opposite of what many people expected. Intuitively, you might think that if you push to smaller and smaller scales, like turning up the pressure in dodgy plumbing, something will burst. Quantum effects, new particles, extra dimensions, whatever's hiding behind gravity's weirdness should start to leak through. The sub-millimeter range looked like a promising crack. Instead, that regime looks boringly classical. The fabric of space-time, as far as these experiments can tell, is well described by Newton plus Einstein even when you probe down to tiny distances. No sudden change in how test masses attract each other. No obvious breakdown that points you to a simple modification. That doesn't mean there is nothing new to find. It just means that easy routes are being closed off. If there are extra dimensions, they probably show up at much higher energies or much smaller distances than we can reach in a lab. If there are new forces, they're either much weaker than gravity at these scales or coupled in very strange ways. If dark matter or dark energy fiddle with gravity locally, they do it below the current noise floor or in more complicated regimes. So gravity, even when you poke it at 50 micrometers with micromachined metal and lasers, still looks like the same geometric field you see in orbit calculations and black hole images. No obvious glitch, no clear, here is where the classical theory dies. That pushes the real clash to a different arena. Not small distances in a quiet lab, but extreme curvature and extreme energy, where general relativity and quantum mechanics both have to matter at the same time. That's the domain where black hole entropy, Hawking radiation, and the Planck scale live. If gravity won't crack under torsion balances and micrometer gaps, then the question shifts. At what point does the smooth fabric of space-time itself stop being a good description and demand a quantum replacement? Right now, you live with two different rulebooks for reality that don't talk to each other properly. One is general relativity, smooth space-time, curvature, gravity as geometry. The other is quantum field theory, discrete particles, fields with quanta, uncertainty and probabilities. Each works insanely well in its own domain. Together, they clash. If you try to quantize gravity the same way you quantize electromagnetism, you get a mess. The math blows up with infinities you can't cleanly remove. Black holes make it worse. In classical GR, information that falls into a black hole can disappear behind the horizon forever. In quantum mechanics, information's not supposed to be destroyed. Put the two together and you get the black hole information paradox. Either quantum mechanics breaks, or our classical picture of space-time and horizons is incomplete. This is not a small technical annoyance. It is a direct statement that at some scale, the smooth fabric story of space-time fails. You cannot just keep extrapolating general relativity down to arbitrarily small distances and up to arbitrarily high energies and expect it to be fine. Something has to change. Physics gives you a rough scale where you know things have to go quantum, the Planck scale. You can build it out of three constants: Newton's gravitational constant, the speed of light, and Planck's constant from quantum mechanics. Combine them and you get the Planck length, about 1.6 times 10 to the power minus 35 meters. You also get a characteristic energy, the Planck energy, around 10 to the power 19 giga-electron volts. Those numbers are stupidly extreme. The Planck length is so small that if a proton were the size of the observable universe, the Planck length would still be smaller than a person inside it. The Planck energy is wildly beyond what any human-built collider can reach. The Large Hadron Collider works at around 10 trillion electron volts. The Planck scale is a billion times higher than that. So we are stuck. We know that near the Planck scale, you cannot ignore quantum effects in gravity. Space-time itself should fluctuate. The idea of a smooth metric field probably breaks down. But we cannot just build an accelerator to go probe it directly. Instead, we have to look for indirect signatures, traces in the early universe, hints in black hole physics, tiny corrections in gravitational waves, and so on. Black holes are one of the few places where quantum effects and gravity clearly intersect. Hawking's famous calculation treats quantum fields in a curved spacetime around a black hole. He found that black holes are not perfectly black. They emit thermal radiation, and they have a temperature. That temperature is inversely proportional to their mass. Smaller black hole, higher temperature, more intense radiation. That result is weird for two reasons. First, it says black holes have thermodynamic properties, temperature and entropy. Second, it suggests that the area of the event horizon is related to the number of underlying microstates, like the number of configurations of whatever fundamental quantum degrees of freedom are making up spacetime and gravity. In other words, gravity might have a kind of atomic structure at a deep level. On the classical side, general relativity has something called the area theorem. In any allowed process, the total event horizon area of all black holes should never decrease, as long as certain energy conditions hold. That looks like the second law of thermodynamics, where entropy never decreases. Recent gravitational wave observations of black hole mergers have tested this. By measuring the masses and spins of the initial black holes and the final remnant, you can estimate their horizon areas. So far, the final area is always at least as big as the sum of the initial areas, consistent with Hawking's area law and the thermodynamic picture. So, between Hawking radiation and the area theorem tests, you get a strong hint. Gravity is not just geometry. It has hidden microscopic degrees of freedom, and black holes are thermodynamic objects. That screams quantum, even though we don't yet know what the underlying theory looks like. Multiple camps are trying to write that theory. String theory replaces point particles with tiny one-dimensional strings. Different modes of vibration correspond to different particles. In this framework, gravity emerges naturally as one of the vibrational modes. String theory lives most comfortably in higher dimensions and comes with a whole zoo of possible compactifications and dualities. It gives you a mathematically consistent quantum theory that includes gravity, but it also has a huge landscape of possible universes and not much direct experimental guidance for picking one. Loop quantum mechanics takes a different approach. It tries to quantize spacetime itself, turning areas and volumes into discrete spectra. Space is built from networks of finite chunks. In this view, smooth geometry is an approximation that emerges when you average over many of these quantum bits. Loop models give you predictions about, for example, the smallest possible area, or how black holes might avoid true singularities. But again, we don't yet have clean experiments. Asymptotic safety is another route. It treats gravity as a quantum field theory that might become well-behaved at very high energies, because the couplings flow to a fixed point under renormalization, instead of blowing up. That would mean you can keep zooming in without hitting a fundamental breakdown. Causal set theory says spacetime is fundamentally a discrete set of events with a partial order representing causality, and the continuum is an approximation. There are more. Emergent gravity ideas where space-time and gravity arise from entanglement in some underlying quantum system, holographic dualities where gravity in a volume is equivalent to a quantum field theory on its boundary, and so on. They all agree that gravity must have a quantum description at some level. They strongly disagree on what that description looks like. The brutal truth is that right now we are data-starved. None of these ideas has a clean, unique experimental signature at accessible energies that would let you say, this one is right, that one is wrong. They all reduce to general relativity plus tiny corrections at the scales we can probe. Those corrections are smaller than our current noise in almost every experiment. So most work in quantum gravity is still theoretical, building models, checking internal consistency, looking for hints that line up with black hole thermodynamics and cosmology. That should reset how finished gravity feels. Going from Newton to Einstein looked like a solved arc. Old force law replaced by a deeper geometry, problem closed. In reality, both Newtonian gravity and general relativity are classical limits. They're approximations that ignore quantum effects. For electromagnetism, we already did that upgrade. Maxwell's equations became quantum electrodynamics. For the weak and strong forces, we have quantum gauge theories. Gravity is the one holdout. So, gravity is now the least understood fundamental interaction, not the most. It's the one that forces you to rethink space-time itself, rather than just adding new particles. It's the one that refuses to fit smoothly into the quantum framework that works everywhere else. And yet, before you even reach the Planck scale, there's another place where gravity and quantum and nuclear physics all collide in a way we can actually observe: neutron stars. There, you crush matter to nuclear density, warp spacetime almost to the breaking point, and then watch what happens when two of those objects smash together. That's the next frontier where we can test how far the classical story goes before it finally cracks. How far can you push matter before gravity and the nuclear force start fighting to the death? Neutron stars are the answer to that question, and they're way past anything you can fake on Earth. Start with a normal massive star. When it burns through its fuel, it can no longer support itself with heat and pressure. The core collapses. Electrons and protons get squeezed together into neutrons. If the mass is in the right range, you don't get a black hole yet. You get a neutron star, roughly 1.4 to 2 times the mass of the Sun, packed into a sphere only about 10 to 12 kilometers across. Stop on that number. You are taking more mass than our entire Sun and stuffing it into something the size of a city. The surface gravity on that object is around 100 billion times Earth's gravity. If you drop the marshmallow from a meter above the surface, the energy it released when it hit would be comparable to a large bomb. The escape speed is a big fraction of the speed of light. Space-time is heavily curved, but not so far gone that light can't get out. Inside, the density is at or above nuclear density. Nuclei on Earth are already packed tightly, but in a neutron star, there are no separate nuclei. You have neutrons jammed together with some protons and electrons, and maybe more exotic stuff: superfluid neutrons, superconducting protons, strange quark matter. We don't know yet. The detailed behavior of that matter is described by the equation of state, a relation between pressure and density. That equation of state is not something you can measure in a lab directly, so neutron stars become the only places you can test it. This is where instruments like NICER come in. NICER is an X-ray telescope bolted to the International Space Station. It looks at neutron stars that are spinning and have hotspots on their surfaces. As the star spins, those hotspots sweep in and out of view, producing a pulsed X-ray signal. The shape of that pulse, when it brightens, how sharply, how the energy changes, depends on how gravity bends light near the star and on the star's mass and radius. If gravity is strong, light from the far side of the neutron star can get bent around toward us. That changes how big the hotspot appears and how the pulse looks. By fitting detailed models to those pulse profiles for objects like PSR 0030 plus 0451, NICER can narrow down both the mass and the radius. Once you have several such measurements, you can start pinning down the equation of state of ultra-dense matter. At the same time, you are testing whether general relativity's predictions for how space-time curves near such a compact object are correct. So neutron stars are already a double test of nuclear physics and of gravity in a regime of insane density and curvature. Then you take two neutron stars and smash them together. On August 17, 2017, LIGO and Virgo detected a gravitational wave event now called GW170817. Unlike the earlier black hole mergers, this signal lasted more than a minute in the sensitive band. The frequency swept up gradually as the two objects spiraled together. The masses implied by the waveform were consistent with neutron stars, not black holes. About 2 seconds after the merger signal ended, a short gamma-ray burst was detected from the same direction. Over the next hours and days, telescopes across the spectrum picked up a new source in a galaxy about 130 million light-years away, a kilonova. The gravitational wave signal told us how the orbit shrank and how the stars deformed each other tidally before merging. Those tidal effects depend on how squishy or stiff the neutron stars are, again tied to the equation of state. The arrival times of the gravitational waves and the gamma rays, separated by only a couple of seconds after traveling for over 100 million years, showed that gravitational waves move at the speed of light to within a tiny fraction of a percent. The electromagnetic data from the kilonova showed heavy elements like gold and platinum being forged in the ejecta. The light curve and spectra matched models of neutron-rich material decompressing and undergoing rapid nuclear reactions. So in one event, you had gravity, nuclear physics, and astrophysics all tightly linked. From the gravity side, GW170817 hammered several nails in. First, it showed that gravitational waves propagate through cosmic distances with essentially no dispersion. Their speed does not vary in any measurable way with frequency. That kills off a lot of modified gravity models that predict different propagation speeds or strong frequency dependence. Second, the tidal deformability inferred from the waveform lined up with equations of state that also fit NICER's mass-radius constraints. That's general relativity plus standard nuclear physics surviving a serious stress test. Put all this together and you see what neutron stars really are. The knot where gravity and the strong nuclear force are equally important. In most places, one of them dominates. In a star like the Sun, nuclear forces are tucked away in the core, and gravity is relatively weak. In a black hole, gravity wins completely, and matter crosses an event horizon. You lose direct access to the internal physics. Neutron stars sit in between. Their gravity is strong enough to crush matter to nuclear density, but not strong enough to hide everything behind the horizon. So, by measuring their masses and radii, watching their spins and catching their mergers, you are doing more than testing models of dense matter. You are checking whether general relativity still gives the right space-time curvature in conditions of pressure and density that no lab can reach. So far, it does. The curves fit. The signals match, but these systems are rare, and our detectors are just at the threshold. As we upgrade gravitational wave observatories and build new ones, we'll see many more neutron star mergers, maybe even more exotic objects. At that point, gravity stops being only a thing to test and becomes a high-precision tool to probe stuff we can never touch. So the obvious next step is to ask, if gravity has already turned from downward pull into a way to weigh planets, map dark matter, time satellites, hear black hole crashes, and probe neutron stars, what does the next generation of detectors and surveys turn it into? How far can we push gravity as a tool once we build even better ears and eyes for space-time itself? You've been treating gravity like background noise your whole life. The punchline now is this: we're turning that noise into a full-blown observatory for everything the universe is hiding from us. Next-generation ground-based detectors are the first big step. LIGO was version 1. Coming up are machines like the Einstein telescope in Europe, Cosmic Explorer in the US, and LIGO India joining the network. These will have longer arms, better mirrors, quieter suspensions, and better isolation from seismic garbage. Translate that into plain language, they'll hear weaker signals from farther away and in more detail. Instead of a few dozen or a few hundred events per observing run, you're talking about tens of thousands of mergers per year. Black hole, neutron star, mixed systems, maybe stranger objects. That isn't just more of the same. With that many events, you can start doing population statistics, how black hole masses are distributed, how spins are aligned or misaligned, how often different kinds of binaries form in different galaxies. On top of that, there's the gravitational wave background, the hum from all the unresolved, distant mergers layered together. Right now, it's barely in reach. With better sensitivity, you can map its frequency spectrum and ask whether it matches what you'd expect from ordinary astrophysical sources, or whether there's an extra component that smells like new physics, maybe cosmic strings left over from early universe phase transitions, or processes you can't mimic in stars. So with better sensitivity, you can map its frequency spectrum and ask whether it matches what you'd expect from ordinary astrophysical sources, or whether there's an extra component that smells like new physics, maybe cosmic strings left over from early universe phase transitions, or processes you can't mimic in stars. So ground-based detectors 2.0 turn gravity into a kind of audio survey of the violent universe. But you might notice a problem. They're deaf to really deep bass. They can't hear the lowest frequency waves from the heaviest systems. So the obvious move is, if Earth is too small and noisy, take the detector into space. That's where LISA comes in, the Laser Interferometer Space Antenna. Picture 3 spacecraft flying in a triangle millions of kilometers apart, linked by laser beams. They form a gigantic interferometer in space, tuned to much lower frequencies than LIGO. That frequency band is where supermassive black hole binaries live, and where weird systems called extreme mass ratio inspirals show up, a stellar mass black hole or neutron star slowly spiraling into a giant black hole in the center of a galaxy. Those extreme inspirals are ridiculous probes. The small object orbits tens of thousands of times deep in the curved spacetime near the big black hole before it finally plunges in. Each orbit imprints information about the spacetime geometry into the gravitational wave signal. Decode that, and you're effectively mapping the metric around a supermassive black hole with insane precision. You can test whether it really matches the Kerr solution of general relativity or whether there are tiny deviations. At the same time, every supermassive black hole merger LISA hears tells you about how galaxies grew and merged over cosmic time. Gravity becomes a tracer of galactic history, not just a local force. But you don't always need multi-million kilometer arms. You can also go the other way and shrink the detectors down to the quantum scale and let atoms do the sensing for you. Atom interferometers are basically matter wave versions of LIGO. You cool a bunch of atoms, put them into a quantum superposition where part of the cloud follows one path and part follows another, then bring them back together and look at the interference pattern. The pattern shifts if the atoms experience slightly different gravitational potentials along their paths. That lets you measure gravity and gravity gradients with brutal sensitivity. On Earth, that means you can map the local gravitational field and pick up tiny variations caused by underground structures, aquifers, or voids. You can test the equivalence principle by comparing how different atom species fall. You might even, in the long term, build atom-based detectors that are sensitive to gravitational waves in a frequency band between what LIGO and LISA cover. So gravity stops being just a thing you plug into equations. It becomes a precision metrology tool, like a ruler and the clock rolled into one, with quantum hardware as the readout. All of that is powerful, but the real prize is what gravity reveals about the dark sector, the parts of the universe that don't light up at all. Weak lensing surveys from facilities like Euclid, the Vera Rubin Observatory, and the Roman Space Telescope are measuring tiny distortions in the shapes of billions of background galaxies. Those distortions are caused by foreground mass bending light. From the pattern of those stretches and shears, you can reconstruct the three-dimensional distribution of total matter, including dark matter, across huge volumes and across cosmic time. CMB lensing, the bending of the cosmic microwave background by intervening structure, gives you another handle. It shows how the matter distribution between us and the last scattering surface has grown, which depends on how dark matter clumps and how dark energy speeds up expansion. Combine that with gravitational wave standard sirens, where the wave signal itself tells you the absolute distance to a merger, and you get new ways to measure how fast the universe is expanding at different epochs. Put all of this together, and gravity turns into a microscope for the dark sector. You may never catch a dark matter particle in a lab directly. You may never measure dark energy in a bottle. But you can watch how they bend spacetime and how structures grow under their influence, and that puts hard constraints on what they can and can't be. So step back and look at how far the concept has moved. Gravity started for you as the thing that makes apples fall and keeps you on the ground. Then it became geometry, curved spacetime instead of a pull. Then it became a clock fixer for GPS, a lens that warps images of galaxies, a weight scale for planets and clusters, a microphone for black hole collisions, a survey tool for dark matter and dark energy. The real twist is this: gravity is now our best indirect detector for almost everything we can't see. Dark matter halos you only know from their lensing and dynamics. Dark energy you only infer from how the expansion responds. Quantum gravity hints you only glimpse from black hole thermodynamics and gravitational wave tests of horizon physics. Spacetime curvature is carrying all of that information to you if you build the right instruments to decode it. We didn't just misunderstand what gravity is, we underestimated what it can show us. It's not just part of the background. It's the main channel the universe uses to broadcast its deepest secrets, from the structure of the vacuum to the fate of expansion to whatever sits beyond the classical picture of spacetime. And the more clearly we listen to that broadcast, the more obvious one thing becomes. The force you learned about in school was just a tutorial level. The real game is spacetime itself, and we're only just starting to see how weird it gets. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.